Okay, it's already 12 p.m., so maybe I can start. So I will give a very short introduction about the workshop and also our speaker before our talk start. So let me go to the first page. Okay, thank you for everybody joining our workshop. Our workshop, actually, the pilot talk today. This is actually a part of the workshop, named Processing in-Memory Technology, which is sponsored by the National Science Foundation. It's going to provide a forum for the leading experts in the relevant research of this processing in memory to do the brainstorming of the latest research progress and discuss their vision of the critical challenges that need to be addressed in the future. That also include, four threads such as the circuit, architecture, system, sorry, there's something wrong with it. There should be the application. We do have a few organizers, to work together on this workshop, including Professor Sharon Hu from Notre Dame, Professor Patty from Washington State University, Professor Wolf Neumann from Technical University of Munich, Professor Xiang Chen from George Mason University. He will be also the local chair, and also myself. You can see actually we have organizers from all over the locations in United States and also in Europe. So the workshop will have two parts. The first one will be the pilot talk, which will be given online to boost the community, vitality during the pandemic, because we're not be able to have in-person workshop recently. So that includes 6 talks online. We have already lined up a few of them, and we're looking for more candidate talks to cover every thread of this workshop. That will happen monthly until the next February, so which means we'll have 6 of them. And we will send out information through our email subscription. That's why we require, people to register on our webpage, because this actually it's only provided, to the registered participant, but rather than the public. And we will have the in-person workshop that will be given in next March if everything will go smoothly. I hope this COVID-19 pandemic will pass. That will include invited talk and panels, and also the group discussion, a breakout, and the output will be a report, support to the National Science Foundation, and hopefully they are able to build up some mechanism, to sponsor the relevant research. We don't know yet, but we will try. We'll provide the travel support, for the participants from US, and they will work together to write the white papers. So the more details, will be given on our webpage. Please, monitor the progress of all this on our webpage. So today we will have our first talk, which will be given by Professor Kaushik from Purdue University. He will give a talk entitled In-Memory Computing Based on Machine Learning Accelerator, Opportunities and Challenges. So Kaushik joined Purdue in 1993, and he's currently holding the Edward Tiedemann Junior Distinguished Professorship there. And he also the director of the Center of Brain-Inspired Computing, break, founded by ICRC and DARPA. For the people who may know, this actually won the JUMP Center. And his research interest in neuromorphic computing, emerging computing, mimetic devices, spintronic device circuit algorithm co-design for nanoscale silicon and non-silicon technology and low power electronics. Kaushik has published, more than 700 papers. I really doubt his number. I think he published more than that because this number keeps changing every day in refereed journals and conference, holding 25 patents and supervised 85 PhD dissertations. I think also more than that. It's actually may not be updated one. And I just want to mention that Kaushik is actually my other wiser in Purdue, but that's not the rate I'm repeating. So yeah, to give the talk. So okay, let's welcome Kaushik to give a talk today. Kaushik, are you ready to switch?
Yeah, I can switch. Yeah.
Okay, that'd be great. Yes, thank you.
All right, let me see if I can do it one more time.
Yeah, we can give it a virtual applause, to welcome you. So.
Oh, thanks. Let me see. Yeah, so can you see the slides now? Iran, can you see the slides?
Not yet.
Okay.
Yeah, we cannot.
Yeah, okay.
We
can't see it. Okay, great.
Okay,
great.
now we can.
Okay. All right. Thanks, Iran, for this kind introduction. And so I'll take this opportunity and talk about in-memory computing-based machine learning accelerators. And I'll particularly focus on the opportunities and the several challenges that lie ahead of us. So with that in mind, I'm going to talk about machine learning, and AI certainly has made a huge amount of progress in the recent past, and and it is also scaling across different applications, including image analytics, medicine, media, security, and you name it. And it's also scaling across investments and people. If you really look at the number of papers coming out, the course enrollment, the VC funding, they're all really skyrocketing. And if you really look at some of the machine learning conferences, the number of publications are probably in the range of close to 10,000 in some of these conferences. So there's a huge amount of interest. And certainly it has made a great amount of progress in the recent past too. However, there are several challenges. So if I had to really look at the computational demands and then followed by the technology scaling, if I were to really look at the machine learning computational cost over the years, this is actually a chart which shows the number of operations required to train some of these interesting networks. And the number of operations are given in terms of zeta operations, which is 10 to the 21, which is really, really huge. So if I were to, for example, take NAS, which is the network architecture synthesis, on something like a transformer or a big transformer kind of architecture, it turns out you need 5 to 10 zeta operations. So the machine learning has a humongous computational cost. And on the other side of it, if I were to really look at technology scaling, turns out Dennard scaling has ended. And if you really look at this chart, which basically shows that the general purpose systems have hit a performance or an energy wall, so to say. So the latest trend has really been the domain-specific accelerators. And there's several examples of that: the Google TPU, the Microsoft Brainwave, the NVIDIA Tensor Cores. Now, if I were to really go now towards the edge intelligence side of things and really look at the efficiency gap, so we did a very simple-minded case study looking at object recognition in a smart glass with the state-of-the-art accelerator. And so in this particular case, we looked at Google Edge TPU and looked at an architecture, which is in this particular case, using the smart glass to be able to do object detection and recognition using RetinaNet DNN. Turns out if you do the analysis, and I'm not going to go into the details of it, but it turns out under ideal conditions, the time to die for the battery is going to be about 64 minutes. But if you really consider all the the actual environment, the battery life is probably going to be about 20 to 30 minutes or so. So that's sort of certainly not sustainable. So what are the issues? Why can't I get good performance? Turns out there are several reasons. The inefficiencies come from using not the right kind of algorithms. Brain certainly is very efficient, and we don't understand the different algorithms that are being used in the brain. On the other side of it, we also know that the hardware architecture of the brain is certainly quite different from what the von Neumann architecture is. Finally, we certainly don't have the right kind of circuits and devices maybe that we're using for some of these applications. So to that effect, today I'm really going to be focusing on the hardware architecture, circuits, and devices. And as I said, if I look at AI hardware and the circuits and architecture that can efficiently implement some of these algorithms and possibly embody the computing principles from the brain. And as I mentioned, the hardware of the brain is certainly unlike a von Neumann computing. There's a lot of computation that goes on in the memory itself. And so there's a need for thinking about, in or near memory computing. And certainly there's a good amount of approximations and other kinds of stochasticity that goes on in the brain. And if we can capture that in the hardware itself, that is also potentially can help. And finally, if we can use devices or neuromimetic devices and the proper interconnects, that can potentially help a lot. So to that effect, if I to really see where we are today, the multi-cores and GPUs and the different accelerators are coming up, there's a huge amount of energy gap that exists between the brain and today's hardware architecture. Now, in order to go closer and closer to to have better efficiency, the question is, can I really think about doing near memory or in-memory computing, use the kind of neuromimetic devices, and potentially get a good amount of improvement in energy and computation time. So with that in mind, I'm gonna focus now on in-memory computing. And so if I have to really think in terms of the background in memory computing, I'll just briefly go over that. From the definition point of view, I mean, design approaches, we can think of design approaches that can perform computation close to memory or in the memory itself to overcome the memory bottleneck, the von Neumann bottleneck. And the kind of things that we can implement are possibly simple arithmetic operations like bitwise, operations, ANDs, ORs, XORs, and possibly can do, in fact, even addition operations, fixed point addition, multiply operations, and that turns out to be quite important, as we'll see, for machine learning applications. And also, in some ways, we can potentially implement truth tables, which can implement, for example, functions or transcendental functions in some ways. And if you can embed that with a ROM, there's some interesting possibilities. So the typical systems have much higher compute throughput than memory bandwidth. And this is actually taken from the traditional computer architecture book, where you see basically the efficiency gap that exists between the processors, or the performance gap that exists between the processor memory and the computation units. And finally, if we are to really look at the chips of today, a good amount of chip area is devoted to the memories, caches, register files, scratchpad buffers, and so on, as is shown on the right for, as an example, TPU floor plan. So now if I were to pictorially try to look at in-memory computing, then I can potentially look at a memory and a standard memory, and that would have a bunch of bit lines and word lines connected in an array. And this could be a 60 SRAM cell, or it can be a crossbar array. And in general, for such a standard memory, what you would like to have is the standard peripherals at the bottom, which are the sense amplifiers for the 60 SRAM cells or caches that we're familiar with. On the other side of it, if you are to really think in terms of doing some bitwise operations, for example, AND operations, NAND operations, or XOR operations, as an example, which we'll talk about later on, turns out you might actually have to turn on 2 word lines. And there's several issues that can happen if you turn on 2 word lines simultaneously in a 60 SRAM cell. That may not work well, so there's some modifications required. But in some of these cases, if you are able to actually turn on a couple of these word lines simultaneously, you might be able to get some interesting operations, and you need a better kind of sensing capability. And finally, if you're able to actually turn on a multiple bit, word lines together and do some sort of analog computation, you can potentially get dot products or matrix vector multiplication. So with that in mind, the question that comes up is what kind of devices am I going to be using? To start with, and it's going to be easy to see. That's why I'm going to talk about the non-volatile memory devices, and some of these are the emerging devices. So I'm going to talk about, and if you're using some of these emerging devices, can you really do an effective in-memory computation? Hopefully better than what you'd be able to do with the standard 60 or the 80 cells, CMOS cells. Now, I'm going to follow that up by talking a little bit about SRAMs and how SRAMs can potentially be also used in some of these in-memory computation. Of course, the amount of area required for doing these computations would go up a little bit with SRAMs, or in fact, quite a bit. And then finally, I'll talk briefly about ROMs and embedding ROM into a RAM and potentially be able to do some, again, near memory or in-memory computing. So with that in mind, I'm going to start with matrix vector multiplication. And why matrix vector multiplication? As I mentioned that I'm going to focus on deep learning, and deep learning needs a lot of matrix vector multiplications. And to that effect, and this is actually a chart from IBM, which shows different application or workloads, like looking at speech, language, vision, implemented on different kinds of networks, like the VGG and the AlexNet for vision, different kinds of LSTMs for natural language processing, and so on. And it turns out what is important to see here is the red bars showing that the GEM operations, or the generalized matrix vector multiplication operations, turns out to be are the majority operations that you end up doing, and hence there's a need for really optimizing that if we can. So the challenge certainly is to maintain the sustaining the deep learning's insatiable computing demands. We probably have to make it more and more efficient. So with that in mind, as I mentioned earlier, I'm going to start with the non-volatile technologies and then go into CMOS as an option for in-memory computing. And then partly because of the fact it's easier to see how some of these non-volatile technologies can potentially be useful in in-memory computing. There are plenty of these devices that I'm showing here, very colorful devices. Some are in their nascent form, some are a little more mature. And to that effect, what I'm going to be really talking about is, or at least concentrating more on RRAMs and PCM kind of devices, which are reasonably mature, but there are several issues associated with these devices, or STT-MRAM kind of devices, and so on. Are reasonably more mature than some of the other technologies that I'm showing on the left. So how do these different technologies compare as an example with CMOS SRAM? So to that effect, I'm looking at PCM, RAM, magnetic tunnel junctions, and CMOS. And what it really shows is that what is important to note is the fact that if I were to really think in terms of the cell area, the PCMs can be quite small, and that turns out is quite important. They possibly in the range of about 16 f², whereas magnetic tunnel junctions, depending on the kind of flavor of magnetic tunnel junctions that you use, they can be all from anywhere from like 30 to 40 to 80 f². And on the other side of it, if you're to really think about the CMOS, that's in the range of about 160 for 60 cells to about 230 for the 80 cells. Write energy, again, quite large for some of these technologies like PCM and RRAMs. And more importantly, it turns out that the endurance of some of these devices are actually quite a bit smaller than CMOS technologies or the MTJs. And that actually plays a very, very important role, because most of these, even if I'm to use PCMs and RRAMs, most of the time we're going to be talking in terms of inference and assuming that the training is going to be done in the cloud. But the good thing about some of these technologies are the fact that I'm going to be using, their cell size is low, and there's a potential that you actually can have very high density memories, on-chip memories, and you can potentially avoid having a DRAM. So with that in mind, I'm going to focus on these technologies first, followed by the CMOS. So with that in mind, let's think in terms of non-volatile memory crossbars. And here I'm showing a crossbar with the inputs coming from the left, and the outputs are available in the columns. And if I to really look at the crossbars in a little more details, each of those devices, which are shown in terms of a conductance as G11, G12, and so on, these could be a PCM or could be an RAM or a magnetic tunnel junction kind of device. The inputs which are coming in are voltage, and the outputs that you get in each of those columns are a summation of VI times GI, which is basically the current, or which you end up getting is basically the dot product. Now, what I'm not showing in this figure are the access transistors, which is actually shown in the top figure. And these access devices turns out to be quite important. And in fact, there's a lot of work which is going on. I mean, you can certainly use this access device to be a standard transistor, but there's a good amount of work which is going on having selected devices and a proper selected devices. And as I mentioned, these devices, the access devices could be any one of those technologies that I talked about. And again, later on, we'll see that we can also replace some of those with CMOS transistors or 60 or 80 kind of cells, and that can also be used, albeit with a lot of increase in area. Now, on the other side of it, you can potentially think of these crossbars, and a bunch of these crossbars. They have inputs which are coming in terms of, let's say, voltage, and the output is in terms of current. Now, when you try to communicate with other crossbars, there's a need for the communication to be done in the digital domain. So one can think of is having at the output of these crossbars, digital to analog converters, or rather analog to digital converters. At the input to these crossbars, you can have digital to analog converters. Now, with that in mind, you can potentially think of an architecture or a tiled architecture where you have a bunch of these crossbars connected through a network on a chip kind of system. And so with that in mind, one can do various computations. And at the bottom, the architecture that I'm showing is a little simplified version of an architecture, which I'm going to go into a little more details of, where how such an architecture can potentially be. So one can now think of architecture with a spatial architecture with scalability, and where one can think of a tiled architecture. And in such a tiled architecture, what I'm really showing is there are different cores, and each of those cores, core 0, core 1, core 2, and so on, which are in a particular tile. And each of those cores contain these crossbars that I just mentioned. And I'll go into a little more details of these cores, but for the timing, let's assume that you have a bunch of these cores connected together into a tile. There's some shared memory in each of those tiles, and also even in the cores, and they're connected through a network on a chip. Turns out such an architecture is quite amenable to data level parallelism and can potentially be quite efficient for ML inference. But in order to see a little more details of these crossbars and how these crossbars play a role in determining what the architecture should be, let's go into a little more details of these cores. But before I go into the cores, let's talk about something called bit slicing, which is going to be in terms of weights and inputs. Now, let's revisit the crossbar one more time. And what I'm showing here is this crossbar with these inputs coming in terms of voltage, and the output of these crossbars, which are from the columns. You have these ADCs, and each of those devices can potentially again be RAM, PC RAM, or other kinds of devices. And each of those devices can implement them. These are analog memories, so potentially they can implement, for example, a device can implement 4 bits or 2 bits and so on. Now, when it comes to some of these, due to technology constraints and to having a reasonable reliability for sensing, you might not be able to actually implement a large crossbar, and you might have to, and each of those devices might only be able to implement, for example, 2 bits as an example. Now, if I'm able to, so what I have to do then is that if I have to implement 4 bits, then I would need 2 crossbars. So what I end up doing then is on the showing is I end up doing a weight slicing. On the other side of it, if you look at the inputs are coming in terms of a voltage, and the voltage can be represented now in terms of a bit stream. and they're going to, and that bit stream could be, representing 101 and so on. And so some bit slicing is also done at the bit level. And so bit slicing and weight slicing would enable you to end up using low precision crossbars and low precision DACs. And at the end of it, using these low precision crossbars and low precision DACs, you can potentially compose high precision, matrix vector multiplication units. Now let me now go into these cores. As I remember, I showed this architecture, this spatial architecture. It's a weight stationary architecture because that turns out to be most important because of the kind of devices that I'm using, and I'm not using DRAM. And now one can think of a heterogeneous core, and each of those cores, as I mentioned, has the most important block. Turns out that block is basically the matrix vector multiplication unit. Along with that matrix vector multiplication unit, you certainly have the digital to analog converters, the analog to digital converters. Turns out each of those cores would also require some vector functional unit and some scalar functional unit, and finally, a little bit of memory. So now if I have to really think of doing, for example, a multi-layer perceptron, the first thing that I would like to do is that the inputs which are coming in, right? And then I'm going to do a matrix vector multiplication, which in this particular case shown as z equal to mx. And then finally, I need to do some thresholding operation, which is basically as shown as a sigmoidal function that I need to do. So one can think of now MLP mapping into one MVMU, right? For the thing that you have to do is to load the inputs and a weight stationary architecture, and you load the inputs, the matrix vector multiplication is done, and the ALU basically that's that sigmoid activation, and you store it back into the memory. Now, there are a few issues that one has to look at. And due to technology constraint, as I was mentioning, that you may not really be able to implement a really large crossbar, right? You may not be able to actually implement a 256 by 256 crossbar or a 512 by 512 crossbar. It turns out if you're able to do that, there are some advantages in terms of area and also energy consumption, but that becomes difficult. So now what you might have to do is that you take this MLP and you have to now map it into a multiple of matrix vector multiplication unit or cores. So then what would that require is that you'll have different partial sums, and you have to add up or accumulate all these partial sums together. And for that, these cores have to communicate with each other. So if that is the case, then when we're trying to implement large matrices, that would require more data movement to compute effective the matrix vector multiplications. And these data movements across the different cores can also turn out to be important. So not only that, not only the fact, I have to calculate these MVMUs, but depending on how we, partition them due to technology constraints, turns out I will actually have, data movement across cores. So the wish list that I'd like to have from the device perspective, when I'm designing, is to have a device to have a high on-off ratio. And the reason why that is important is that if I have a high on-to-off ratio, I can potentially think of having better sensing capability at the output and of these crossbars, or better ADCs. And at the same time, I'm going to be able to have larger crossbars. Remember, I haven't talked about sparsity. Sparsity can also let you have larger crossbars. Now, device linearity, that turns out to be quite important, especially when you're writing into these devices. And a few other things which are also important is I'd like to have high endurance. If your endurance is not high enough, maybe such an architecture is not going to be suitable for training. And then at the end of it, for higher density, I'd like to have multi-level cells. And again, some of these devices, for example, a magnetic tunnel junction may only implement, for example, a single state. At the macro level, for these crossbars, what I really want is a large crossbar size. At the end of it, we'll see that the peripheral turns out to be the dominant component in terms of overhead, power consumption, area, and so on. So low peripheral overhead turns out to be very important. I need a good selected device. For writing, when I'm writing into these cells, a few other things that are also important, because I'm going to be using the neurons and at the input and output of these crossbars, the source and sink resistance of these neurons also become quite important. And finally, at the end of it, the line resistance would also play a role. And then finally, from the architecture point of view, an algorithm point of view, what I really like to have is a minimal data movement, right? As I mentioned, we might have to break up your MVMs into smaller crossbars, and for that, you certainly need the minimal data movement. Training on mapping of this architecture becomes important because there are several non-linearities and other issues that come into picture, and non-idealities that come into picture, which I'll talk about. So training and mapping on these architecture also become important. And finally, if I have enough sparsity, that can lead to larger crossbars and certainly help in terms of better energy consumption. Now, from the device point of view, if I were to really think in terms of, as I mentioned earlier, compared to CMOS, these devices have some advantages, and non-volatility is one. High density, that turns out to be quite important because I'm assuming that there's not going to be, DRAM. Low leakage, also very important, comes from non-volatility, and are certainly very capable of in-memory compute. The cons, of course, are the fact that the write energy and the write latency can be high. And as I mentioned earlier, for some of these devices, it turns out the endurance can really be a problem. For example, the PCM, the RRAMs, the number of cycles potentially can have is quite low. Current devices are highly nonlinear, and maintaining a good I onto RF ratio is limited to about 10x or so when it comes to some of these devices. And as I mentioned, poor endurance is also a problem. And it's also very difficult to get a cell which is going to have more than 4 bits per 4 bits. It's not that reliable yet. Challenges from the macro point of view. As I mentioned, the NVM crossbars can have various non-idealities. And that can include, for example, the parasitics that I talked about. The non-ideal device characteristic, the devices may not be linear, and non-linearity of these devices can play certainly a very important role. And you have these source resistance, sink resistances, and other kinds of parasitics like the line resistance. The non-idealities can introduce a varying amounts of functional errors depending on the kind of input voltage and conductance. So what we did is we looked at some realistic crossbars and plotted the ideal current that I'd like to have versus the current due to all these non-idealities that I end up getting. And I'm actually showing it as a scatter plot, which is shown in blue. The ideal one is certainly going to be a 45-degree line, but the non-ideal one, as you can see, can deviate quite a bit under larger voltage or current conditions. And that turns out to be an important issue when it comes to mapping or training on the training in the cloud and bringing that trained data into your devices. As I mentioned, errors increase with the higher crossbar sizes. Few other challenges: ADCs consume a good amount of area and power consumption, and as you can see, for some of these crossbars, your energy is really dominated by the crossbar energy, the ADC energy. And similarly, when it comes to area, again, the area is dominated by the ADCs again. Now, a few things. So how do I model? So in fact, in order to design, then I have to be able to model these crossbars well. The non-idealities do play a very, very important role. And if you try to actually, implement it using a linear model for these resistive elements, and if you design, come up with a crossbar with these linear elements, you are bringing lots of errors. So to that effect, it is really, it's important to consider the column current, which is actually a function of, the input voltage that are coming in, which is in terms of VI, and the conductance GI, but the conductance in this particular case are also a function of voltage. So it turns out modeling such a crossbar becomes a little difficult if you do consider, as I mentioned, linear crossbars, you do bring in a lot of errors. So the function f for these when it comes to the current is a data dependent and is a nonlinear function. So to that effect, what we decided to do is that, is it possible that I actually model these crossbars using a neural network? So in other words, neural networks are efficient tools for capturing close interdependence of its inputs, and but they're not good in when it comes to multiplications, and that's exactly what we're doing. So we had to make some adjustments, and I'm not going to go into the details of it. This paper appears at DAC this year, but turns out by taking proper ratios of the ideal current and the non-ideal current, what one can do is actually one can model these crossbars using a neural network. So in other words, what happens is if you have the real crossbars and if you have data available on these crossbars, you can use that data from the measured data to actually build your neural network, or you can run a large number of these SPICE simulations, which can actually capture the data, and you can use that data for training this neural network. So GenieX is a generalized approach to emulating these non-idealities in memoristic crossbar, and one can use that for determining the nonlinearities. And when you're actually doing inference, for example, you can use such models to do the proper inference. And in fact, it can also be used in training. So challenges from the architectural side, turns out it's also quite important. Remember, we talked about the cores, which are shown there, and the cores are, a few of those cores do end up forming a tile, and the tiles now are connected through a network on a chip kind of architecture. So each of those tiles potentially are going to send information to other tiles. They send information to different tiles, and depending on where these tiles are, you can have different amount of communication required. So data movement across between MVMUs, partial sums, activation is frequent, and the cost of these data movement increases across the hierarchy, going from core tile to the chip. And this is basically showing an example of how much of those communications are, and the communication costs are between intra-core, intercore and inter-tile communications, and that can vary quite a bit. So the idea is that, if I'm able to map my crossbars properly across this architecture properly, I can reduce that cost. So mapping of workloads to these instructions become quite important. And as I mentioned earlier, that while crossbars are an integral component of these architecture that I'm talking about, it turns out that there are other functions. Those are also very important. Like, for example, intercore data transfers, the scalar functional units, the vector functional units. Of course, at the end of it, the MVM crossbars do take up a reasonable amount of computations and workloads, but these are all very, very important. So MVMUs, or in other words, MVMUs alone cannot execute the ML applications. There are other vector operations that are important, and other transcendental operations that are also important. So what are the potential solutions to what we've been talking about? Turns out it is certainly important. We talked about crossbar non-idealities, modeling of these crossbars. So considering some of these non-idealities and non-linearities. So if I were to really think of inference, training, let's say if it's done in the cloud, using floating point weight, and then you have to transfer that into this tiled architecture. This tiled architecture that we used is called Puma, which was developed in our group. So what you have to do is you have to do proper tiling and bit slicing. As I mentioned earlier, again, the crossbar size have to be mapped into these architectures, and one can then use the crossbar model, like the GenieX that I talked about, to be able to actually do the forward pass through the network. So during the forward pass, actually, you have to call up these, the neural networks. It's not cheap. It does cost you quite a bit in terms of time, but certainly you can do it in the forward pass of your inference. Now, for training, what is also important to understand that I didn't talk about the training part of it, the training has to comprehend some of these non-idealities. And if I'm able to actually comprehend these non-idealities and non-linearities during training, then certainly I can improve the accuracy of my training. Otherwise, if I do not comprehend that, a lot of times you'll find out that your accuracy suffers quite a bit. How to improve the hardware efficiency then? As I mentioned, the architecture, the tiled architecture Puma one can use, and that can certainly use inputs coming from PyTorch, Caffe, and so on into that goes into, for example, an integrated open neural network architecture exchange kind of format to execute the models. There's a Puma compiler, which is basically the compiler to that tiled architecture, and the Puma instruction set architecture, and finally a PIM simulator. And that's all available in the GitHub if you're interested in using it. And at the end of it, such a hardware software co-design to optimize data reuse, as I mentioned, to support different operations, can potentially lead to low energy, reasonable latency, and high utilization of these crossbars. So if I have to now revisit the modeling and the simulation ecosystem, to start with, you need the right device models from PCM, RRAMs, and so on, or CMOS. The circuit models, you can use crossbars with the right kind of R on to RR ratio. And from there, the crossbar models can certainly use an analytical modeling. Like, for example, using linearity assumptions of these devices, one can model it, not considering the access devices, and that would give you a reasonably simple model, but can potentially bring in a lot of inaccuracies and accuracy drop in terms of the neural networks. But a statistical modeling, like what I just talked about, using GenieX for the would certainly give you much better accuracy for these neural networks. So the architectural model, one has to think about functional modeling then. That would certainly use with starting with this MVM, the matrix vector multiplication unit, doing proper tiling and bit slicing, and then finally going into the performance modeling using this Puma kind of architecture and using the simulation environment. So that's, one can potentially think of such a modeling and a simulation ecosystem for that. So with that in mind, what we did is we actually did an analysis of such an architecture, and then tried to compare that with Skylake and Pascal. And we looked at the multi-layer perceptrons, deep neural networks or wider neural networks, LSTMs, and also the convolutional neural networks like the VGG16 and VGG19. Interesting to notice that I didn't consider in this particular case any non-idealities and non-linearities. So things were simple, but with that in mind, one can see it's possible to get a good amount of improvement compared to, for example, some of these GPU architectures. So with that in mind, I mean, so far what I have talked about is, and these results are inference energy with a batch size of 1. So with that in mind, what I wanted to do in the first part of the talk is talk about some of these non-volatile technologies and how in-memory computing, in particular actually matrix vector multiplication, can potentially lead to an architecture which is a tiled spatial architecture, and these architectures can lead to an improvement in energy consumption, especially for inference energies that I'm showing for a batch size of 1. There are several challenges, as I mentioned, the non-idealities, non-linearities, ADC costs, those are going to play a major role. And unless we're able to actually have the reliability of some of these devices up, certainly it's not going to work that well. And certainly it was not going to work for training, but for inference, some of these devices do make sense. So I'm going to change gear a little bit. And for the rest of the time, briefly talk about CMOS as an option for doing in-memory computing. So with that in mind, I'm going to talk about not only SRAMs and DRAMs, and in fact, in some cases, DRAMs can also be quite important. So I'm going to talk about a few of these things: bitwise Boolean operations in SRAMs, dot products, lookup tables, and so on. So let's start with the bitwise Boolean operation, and very quickly want to go over some of these. As I mentioned earlier, that when I'm trying to do bitwise Boolean operations, I'd like to simultaneously activate two word lines in this particular case. The problem with the standard 60 cell is the fact that if you really try to activate two word lines simultaneously, there's going to be a path from VDD to ground, a direct path from VDD to ground, and that's a problem. So in other words, what you then have to do is you have to do, for example, maybe a staggered word line activation to avoid short circuit between cells. So with that staggered activation, what one can do then is, look at various options of storing, for example, 0, 0, 1, 1, 0, 1, and 1, 0, in each of those cases to be able to do vector operations, NAND, NORs, and so on. And it turns out that by putting an asymmetric sense amplifier at the bit lines that I'm showing there, it's possible to get NAND, NORs, and with a little bit of logic there, you can also do XOR operations. So it's possible to do that. But as I mentioned, you would need staggered bitline activations. But on the other side of it, if you really think of an 8T cell, and I'm not going to go into the details of 8T cells, but it suffice to say that in the cells, the read and the write are decoupled. And the read part of it is shown by these two transistors, M1 and M2, and the write is done usually in the standard 60 configuration, as I'm showing on the top. With that in mind, what one can potentially do is one can think of these cells again to be able to do bitwise operations. So I'm showing two read word lines which are activated in yellow, and what one can do is one can look at the equivalent circuit here, and which is basically the read part of the circuit with the read word line 1 and read word line 2, and I'm trying to do these bitwise operations. And it turns out, I can pre-charge the bit lines to VDD over 2, and depending on whether the two, the storage cells are storing both zeros or ones, you end up having at the output of VDD over 2. And if you don't have that, I mean, on the other side of it, if you have storage to be 0, 1 or 1, 0, turns out that you'll have either a path to ground or a path from VDD, and that makes the output to be either, in case of 0, 0, 1, 1, the output is going to be VDD over 2, or in case of 1, 0, it's going to be VDD minus VT of the top cell, or just 0. So in other words, if you have a sense amplifier at the output, which can distinguish between these different states, then you can either get a NAND or a NOR operation, or by actually putting an extra gate there, you can get an XOR operation. So with that in mind, what one can do is then with an SRAM cell like that, one can do bitwise operations, and by putting extra circuitry at the bottom, one can also do add operations, addition operations, and so on. And it's also possible to actually feed back in a single cycle to a cell back to another cell to be able to write the output of these output of your bitwise operations to another cell. Now, so potentially now we can think of a system to do in-memory computing, where in a conventional instruction that you'll do is, you do have a load, two loads followed by an add instruction and then a store instruction. So you can replace all those in case of doing in-memory computing. So you can potentially think of a CIM add, which is a compute in memory add, which is going to be doing this operation using one shot. To that effect, that's one possibility, but also one can do other than machine learning kind of applications. They can also do, for example, XOR operations, as I mentioned, XORs can also be good for machine learning when it comes to, for example, certain kinds of operations, but something came up here, I don't know how. But anyway, it's possible to actually do AES encryption and one can potentially have a good amount of improvement if you're able to do these in-memory XORs doing AES encryption. I don't know why this line has come up, but anyway, it's also possible to ignore it, this red line over there. I can get rid of it, but that's going to take a little bit of time. But one can also do interleaved word lines to do in-memory vector computing operations. So in other words, what one can do is each row has two read lines, two read word lines, and one can also have the bit lines connected to every other cell. So if you do that, it turns out you can take two word lines in a 60 cell and combine them together or activate them together to be able to do bitwise operations. And the reason why you're able to do that is because these two word lines per cell are connected alternately to each of those cells. So now you're able to do bitwise operations by interleaving, and you don't have to stagger the bitline activations. Few other things one can do is, one can also do, for example, dot products in these 80 cells, or in fact, even the 60 cells with staggered bitline operations. So I'm going to give you an example of that. Again, when it comes to dot products, you have to have multiple word lines to be activated. And it turns out it's easy to do that in that 60 kind of cell, or rather 80 cells which have decoupled read and write, so you can simultaneously activate them. And if you do that, turns out you can potentially think of, and I'm showing the read part of the cell. And if you look at the read part of the cell, and I'm actually activating, to read part of the cell, it turns out it's possible to actually potentially think of having an, read word line, which can be connected to V input, which is in this particular case, I'm showing an analog value. So V in 0 and V in 1, which are shown on the right. And I'm only showing the read part, the right part of it, which is in the 60 cells, are not shown for these 80 cells. One can also think of the MSBs to have higher weightage. So the access transistor for each of those cases can be, if it's an MSB in this particular case, can be 8W, and the LSB can be W. So you're going to pay in terms of area in this particular case. And then at the output of it, you have a sensing circuitry. And if you connect all the bit lines together, you actually end up getting a dot product. A few issues that one has to look at. Certainly when you use these 80 SRAM cells as a multi-bit dot product engine, one has to also think in terms of the effect of line resistance and other non-idealities that I talked about. And here I'm plotting the weight levels versus the voltage levels on the on this graph, where blue basically tells me that there are not much errors. The errors increase on the right and on the top corners, which is red. And what we ended up doing is we actually ended up implementing MNIST in this kind of architecture. A simple data set. But what is really important to note here is the fact that our profiling showed that the neural network has most of the weights closer to the 0 level. And that what it means that the current levels are low and we're mostly in the blue region. And so the error wasn't that much. A few things, these kind of cells are not certainly 60 cells. These 80 cells, you have to you pay in terms of an extra area of about 30%. And also at the same time, as I mentioned, the access transistors, depending on whether it's an MSB or LSB, are going to be large or small, and that also going to add to the area. So multi-VT cells can potentially be exploited to reduce the cell area. A few other things I'm just going to quickly talk about. I talked about ROMs being able to be used for in-memory computing in some ways. So one can use lookup tables to implement, for example, transcendental functions or the math tables as an example. And but ROMs do end up taking area, extra area, and we didn't want to do that. So is it possible that I can embed a ROM into a RAM, if that makes sense? So in other words, what I'm going to be showing is an example of, let's say, an STT-M RAM in this particular case. This STT-M RAM can also be replaced by, for example, an RRAM or a PC RAM. By the way, we can also do SRAMs, the standard CMOS SRAMs. I'm not showing that example here because that's a volatile memory technology, and you need a few extra steps to understand that. So if you're interested, I can talk about it, or rather explain that later, or I can give you a reference. But what I'm really showing an example of a STT-M RAM or an RRAM. And what is really interesting to note here is that I have these access transistors, and I have bit lines. In this particular case, the bit lines are the source lines which are shown there. Now, what I'm really showing is that I have, these are STT-M RAM cells, and I have two bit lines which are connected. The connections to these bit lines are either to one of the cells, but not to both the cells. And the connections to these bit lines determine what ROM value it's going to store, right? Now, when I come to RAM operation, what I'm going to do is I'm going to make both bit lines active. They might be able to then, I might be able to store any information into these magnetic tunnel junctions or the PCMs. However, when it comes to ROM operation, I'm going to activate one of the bit lines. And when it comes to standard RAM operation, the read-only memory operations, I'm going to activate both the bit lines when a standard word line is activated. Okay. However, and that I'm going to get the RAM data out of it. But when it comes to ROM operations, I activate the word line, but I activate one of the bit lines, not both bit lines. And as you can see, if the cell is connected to a bit line, you're going to see a resistance. If the cell is not connected to a bit line, you're going to see a completely different resistance, which is much, much higher, an infinite resistance. So having two sense amplifiers over there, you might actually be able to say whether I'm storing a 0 or a 1. So what the storage in the ROM is in terms of basically what the connections are to these cells, to the bit, which bit line it is. And again, that can store different kinds of transcendental functions and so on. DRAMs, can I use DRAMs? It turns out it can also use DRAMs for in-memory computing. And I'm going to take an example of a bit serial addition in this particular case, where it's a majority-based vector addition. C out and the sum is a majority of 5 of these, whereas C out is a majority of A, B, and C input. The storing the data in a DRAM, what I'm showing is that the data is stored in column-based fashion. And I have to add a few rows for the computations that I'm going to be doing. And these extra rows are given in terms of these red array that I'm showing. That actually puts an overhead about 1% or so, or 1% or less. The results of the A and B are stored in that in the same column, and it's possible to do massively parallel vector additions and no need for carry shifts across the bit lines. So to that effect, let's try to see how a multiple row activation to calculate the majority operation of A, B, C, D, and E can be done. And this is actually showing an initial state of a DRAM, storing zeros and ones as shown there. And then, of course, as I enable the word lines get activated. And what you get at the output of the bit line is, to start with, what the initial state was, this bit line was activated, had, the precharge to, let's say, half VDD. And in this particular case, what I'm going to get is, half VDD plus some delta V. And the delta V is going to depend on how many of those bit lines or rather the majority function that I had, how many were zeros and how many were ones. So what I really end up doing is delta V is going to be positive or negative depending on the majority function that I have, right? And this majority function now determines basically my sum, which I'm storing using that cell. So at the end of it, I'm also need to calculate so far we talked about sum. You can also do C out and C out bar calculation for when we're doing the majority sum calculation using dual contact cells. I'm not going to the details of it, but the basic idea again is that I activate the word lines again, and based on what I have in my cells, the majority function, I end up storing that into this dual contact cell. So to that effect, one can potentially think of having data rows, which are data in columns. I actually then I take the data, I activate the data A0, I activate the data B0, which is basically doing these operations, and then I store them into this red area. And in this red area, I'm going to do this, these majority computations, and finally store the sum in the location shown there, right? So it's possible to do these kind of operations, and at the end of it, for n-bit vector additions, I need 4 n+1 operations which are needed. The good thing about it is that it can. We looked at a case study of computing DRAM-based, k nearest neighbor problem, and the k nearest neighbor, checks k closest samples, and the query vector assigned to the group that holds a majority among those k samples. To that effect, what we did is the interesting thing to note is that it mainly consists of 2 computation stages: distance computation and the global, top case sorting. The sorting part of it is done in the host processor, and the DRAM for the in-memory DRAM computations, the Manhattan distance is computed in the in-memory DRAM. We looked at a processor kind of architecture with an L1 and L2 cache with a main memory as shown there. And we did an analysis of it showing a baseline application where we were not doing in-memory computing in the DRAMs versus this proposed system. And what it really shows is that it's possible to get about 1.7x performance improvement because of being able to do that computation in the DRAMs. So with that in mind, I know I'm out of time, but in conclusion, while possibilities of achieving large improvements in inference latency and energy is possible using these in-memory computing techniques, what I really want to underscore is that there are several challenges. The crossbars have several different non-idealities that one has to consider. Device nonlinearity, access transistors, selected devices nonlinearities, the circuit nonlinearities, which include line resistance, source resistance, sink resistance, and process variability. That's going to play a very, very important role. Reliability and endurance of these non-volatile devices are not good. So the training certainly has to be done in the cloud, and inference possibly on some of these devices. There's a high write cost for these NVMs. At the end of it, there's A to D and the D to A converters are absolutely important, and they are the dominant component of power consumption. Nothing comes free. We need to have to divide these crossbars into a tiled architecture. Data movement in some of these between the different tiles or the different cores turn out to be quite important. So mapping becomes important, and you have to see that how much of these data movements end up having, and they add up to these overall performance. Training and mapping to the hardware. There can be potentially degradation over time in some of these NVM technologies that one has to look into. There's certainly need for vector operations and floating point operations that, I didn't consider the floating point operations in any details. SRAMs are large compared to emerging non-volatile technologies. So certainly when you do SRAM-based computations, you have to consider the fact that you're dealing with a lot larger area. So with that in mind, I'm gonna end the talk and acknowledge my students who really end up doing all the work, and I get to present their work. Thank you very much.
Kaushik, thank you so much for the comprehensive talk. If you have a little bit of time, we can maybe take a few questions from the audience.
And I apologize, this little circle, I don't know, or this scratch where it came from, but and all of a sudden I find, hey, it's there.
Don't worry.
It was a little irritating, but I decided not to change it and stop and change it.
Yeah. I think if you want to ask any questions, you can unmute yourself, because, yeah. So I didn't force anybody to be muted, so. Yeah. Any questions from the audience?
Go ahead. I had one question about, you were talking about something like sparsity and the size of the crossbars, like large size crossbars may aid sparsity, something like that. Would you please say that in a little bit more?
Sure. That's a very important question. Turns out that if you look at these neural networks, there are different levels of kinds of sparsity one can think of. You can have weight level sparsity, and pruning and other things can be done for weight level sparsity. But there's also an input level sparsity. And a good number of these inputs are zeros. And if you look at a spiking network, there's a huge number of zeros. But if you're really talking in terms of these, standard deep learning, you find that a good number of inputs are zeros. So if the inputs are zeros, and on an average, if I have a huge number of zeros coming to these crossbars, in other words, when an input becomes zero, effectively, you can get rid of the row, right? So in other words, if I always have, if I can, if I'm really looking at a sparsity of, all the time of 50% or 60% or 70%, in that case, I can potentially think of having an effective crossbar to be larger. So I can potentially say that, hey, I'm going to have a 128 cross 128 crossbar, but only, 60% of these, or rather only 40% of these inputs are going to be active. Does that make sense? So in other words, you can potentially think of having a larger crossbar, or we can think of having a lower precision ADC.
Sharon, do you have any questions?
Yes, I actually would like to hear Kaushik's insight on whether floating point operations really a good buy in terms of putting it in memory computing.
Yeah, I mean, right now the assumption was that it was not floating point computations. Those are separate. A lot of times we do the training in the cloud, and I'm going to bring in this integer-based computations into my crossbars, and so that with that assumption is what I'm really doing here. Didn't really look at the floating point part of it. A lot of these computations, for example, can be done with, inference can potentially be done with 4 to 8 bits. You may not need more than that, but for training, absolutely need.
But I just felt like floating point itself, in terms of computing versus memory, it seems a lot more heavier on the compute side. So I'm just trying to see whether it's really beneficial to do it inside memory, or we just read it out and design a really efficient floating point unit.
Yeah, good question. It all, at the end of it, it all depends. And I said, I mean, if we're able to effectively do certain computations in the memory itself and some bitwise operations and some other kinds of, matrix vector kind of operations which are done there, probably doing it in the memory is a good idea. Though, as I said, the jury is still out there. It is an analog computations, and there are issues. There are issues. There are still various things to be, sorted out.
Yeah. Great. Thanks.
Hi,
this is Arman from Notre Dame. I have a question about this Puma tool that you talked about, and it looks somewhat similar to NeuroSim. I was wondering, what are the differences? What are the advantages and disadvantages regarding trying to emulate?
It is basically an architectural simulator. It's a little bit different. It's an architectural simulator. The architectural simulator basically, if I would go back to, let me see if I can go back. So, now this line is there everywhere. We didn't start with that, but yeah. And a network architecture like that, for example, has a shared memory, right? Has these different cores, data movements. They're basically a simulator to simulate such architectural thing. So what happens is that you have an input that comes in to this architecture, which is going to be given sort of, let's look at this. On the right side of it. Excuse me. So you have the input that comes in from your deep learning tools like there's PyTorch or Caffe, going through an integrated, open neural network exchange kind of format. The Puma compiler basically deciding, hey, which crossbar is going to be mapped where into these architecture, right? And then simulating basically the data movements and so on.
Does it give you the energy and action?
It does. It does give you the energy and the latency, because it can be connected, for example, to a crossbar tool and the crossbar tool can potentially give you basically the energy due to the ADCs and DACs and the total power consumption. And then of course there's other units which are there, which were also we have models for those to be able to determine, what the latency would be and the power consumption.
So I had a quick question. What was the lowest precision you used for ADC to maintain the accuracy?
Depends, for example, if I'm using a 128 cross 128 crossbar, in a lot of cases, we would probably try to use, for example, rather than using a 7-bit ADC, we can use a 6-bit ADC. And the reason is, as I mentioned earlier, if you have enough sparsity, you might actually be able to use such things. And depending on the size of the crossbars, if you're using, for example, a 32 cross 32 or a 64 cross 64 crossbar, it's going to be lower.
Okay, thank you.
Okay, do you have any more questions or? Okay, so if not, I would like to thank Kaushik for the inspiring talk. By the way, Kaushik, actually I wear the Purdue shirt today. Yeah. Now you look at my T-shirt. It says Purdue. Basketball.
Oh, it does. Okay, there you go.
Yeah. Thanks so much for the inspiring talk, and that's the concluded section. We will have the next the panel talk next month, and I hope everybody will be able to join us again. Thanks so much for attending this talk.
Thank you.
Thank you.
Thank you. Thank you for the organizers. Yeah. Bye.
Thank you.